Okay, we're moving on to section 7.4, work done by a varying force. Okay, we consider a particle displaced along the x-axis under the action of a force that varies with position, as shown in the figure on the left here. We can't use our work equation because it applies only when when the force is constant in magnitude and direction. So in figure A, the left-hand side, the red-brown curve shows varying force applied on a particle that moves from initial position xi to final position xf. So imagine a particle undergoing a very small displacement, delta x. That's that little shaded area. The x component of the force, F sub x, is constant over a small interval. For this small displacement, the approximate work done on the particle by the force work is equal to Fx times delta x, for a very small sliver there. If the Fx versus x curve is divided into a large number of such intervals, then the total work for the displacement from xi to xf, that is the initial x to the final x, is approximately the sum of the large number of such terms. The work is equal to the sum of each of those little slivers. Okay. As the size of the small displacements approach zero, the number of terms in the sum increases without limit, but the value of the sum approaches a definite value, which is the area bounded by the fx curve and the x-axis. That's the figure B. So it expresses an integral. The limit as x approaches zero, the sum of x initial to x final of fx delta x is the integral from x initial to x final of fx dx. So the work done by fx on the system of a particle as it moves from x initial to x final is the work equals that integral, the integral from x initial to x final of fx dx. The equation reduces to the previous work equation when fx equals f cosine theta is a constant. Okay, let's move on. If more than one force acts on the system and the system can be modeled as a particle, then the points of application of all forces move through the same displacement, and the total work on the system is the work done by the net force. Okay, if we express the net force in the x direction as the sum of the fx, then the total work, the net work, is done as a particle moves from x initial to x final. Don't know why the dogs are barking. Now, the general case of the net force, the magnitude and direction vary. We use the scalar product. The integral calculated over the path that the particle takes through space. The subscript ext on the work is the net work done by an external agent on the system. If the system cannot be modeled as a particle, that is, the system is deformable, we can't use this equation. The different forces on the system may move through different displacements. We must evaluate the work done by each force separately and then add the works algebraically to find the net work on the system. So notice here on the deformable system how the sum of the work is equal to notice how the sum, the little sigma, not the little, the big sigma symbol is the sum of the forces, the integral of the forces on the inside. It's just a movement of the sum, the sigma from the inside the integral to outside the integral. So you take the integral first and then you sum all of them together. Now let's do an example. The force acting on a particle varies with x as shown in the figure. Calculate the work done by the force on the particle as it moves from x equals 0 to x equals 6 meters. This is rather simplified. example, but it gets the point across. Let's conceptualize it as follows. Imagine a particle subject to the force in the figure. The force remains constant as the particle moves through the first 4 meters and then decreases linearly to 0 at 6 meters. In terms of the earlier discussion of motion, the particle could be modeled as a particle under constant acceleration for the first 4 meters because the force is constant. Between 4 and 6, however, the motion does not fit into one of our earlier analysis models because the acceleration of the particle is changing. If the particle starts from rest, its speed increases throughout the motion, and the particle is always moving in the positive x direction. These details about its speed and direction are not necessary for the calculation of the work, however. Because the force varies during the motion of the particle, we must use the techniques for work done by varying forces. In this case, the graphical representation can be used to evaluate the work done. The work done by the force is equal to the area under the curve from x equals a to x equals c, from 0 to 6 meters. This area is equal to the area of the rectangular section from A to B, plus the area of the triangular section from B to C. So we evaluate the area of the rectangle, 5 newtons times 4 meters, we get 20 joules. Now if we evaluate the area of the triangle, the area of a triangle is 1/2 the base times the height, so it's 1/2 times 5 newtons times 2 meters. We get 5 joules. Now, to find the total work, we just add those two, 20 joules and 5 joules, and we get 25 joules of work. Because the graph of the force consists of straight lines, we can use rules for finding the areas of simple geometric models to evaluate the total work done in this example. If the force does not vary linearly as in the figure, such rules cannot be used and the force function must be integrated. Okay, let's look at the work done by a spring. This figure shows a model of a common physical system in which a force varies with position. The system is the block on a frictionless horizontal surface connected to a spring. If the spring is stretched or compressed a small distance from its unstretched, that is, from its equilibrium position, it exerts a force on the block. And that force is equal to minus kx, where x is the position of the block relative to the equilibrium position, and k is a positive constant, called the force constant or the spring constant. And we'll get to that. In fact, we'll do a couple of experiments. So if you have the equilibrium position, let's say the spring is over here, and here's the equilibrium position. If you push on the spring is going to push back. If you stretch the spring, it's going to pull back in that direction. So that's why we have the negative sign. The Fs equals minus kx. We have the minus sign because the force is in the opposite direction of the displacement. If the displacement is toward the anchor point, the force is outward. If you pull it away from the anchor point, the force pulls it backward. This is known as a Hooke's law relationship. So the force required to stretch or compress a string is proportional to the amount of stretch or compression, and this is known as a Hooke's law relationship. The K measures the stiffness of the spring. A stiff spring has a large K value, and a soft spring has a small K value. And the units for K are newtons per meter. In other words, for every meter, you get a particular force. Now the vector form is already shown. The spring force is equal to Fs in the I direction, and it's equal to minus Kx times I. The negative sign signifies that the force exerted by the spring is always directed opposite the displacement from equilibrium. It's sometimes called the restoring force. If the spring is compressed, the block at point, if the spring is compressed, the block wants to move outward back to the equilibrium position. And if released, it'll move back to that position. If you reverse it, the spring wants to pull it back to the equilibrium position. We'll study more about these when we study oscillations in chapter 15. Now, the work done by a spring, if the block is pushed to the left to position minus x max and then released, we calculate the work done by the spring force on the block as the block moves from x initial of minus x max to x final of 0. We assume that the block may be modeled as a particle, and so the work is equal to the force dot dr, and the force we know is minus kx, kxi, and dxi, and you go through the integral of minus kx dx is equal to 1/2 kx squared. Okay. The work done by the spring, by the spring force is positive because the force is in the same direction as its displacement. Both are to the right in the figure during the time interval being considered. Because the block arrives at x sub x equals 0 with some speed, it will continue moving until it reaches position x max, just because of inertia. Work done by the spring on the block as it moves from x initial equals 0 to x final equal max is as shown. Is that the right one? 1, 2. I think I skipped one. Okay, the work is negative. For this part of the motion, the spring force to the left and the displacement is to the right. So if they're in opposite, the work is negative. The net work done by the spring force on the block is as it moves, the net work as it moves from minus x max to x max is 0. Okay, let's continue. The work done by the spring force on the block as it moves from minus x to 0 is the area of the shaded triangle, 1/2 kx squared. Okay, the figure is a plot of the spring force versus x. In Fs, the spring force is proportional to x. It's a graph of the Fs versus x straight line. The work is the area under the area of the shaded triangle corresponding to the displacement from minus x to 0. The triangle has a base of x max and a height of k max. Its area is 1/2 k x max squared. If the block undergoes arbitrary displacement from x to xi, from x equal xi to x equal xf, the work done by the spring force on the block is the integral of x initial to x final of minus kx dx, which is equal to 1/2 kx initial squared minus 1/2 kx final squared. The work done by the spring force is equal to 0 for any motion that ends where it began. That is, x initial equals x final. Okay, now consider work done on a block by an external agent. As the agent applies force on the block and the block moves very slowly from x initial to of minus x max to x final of 0, as in the figure. The applied force pushes inward and prevents free expansion. Previously, the block was free to move freely. It was the spring that was doing the movement, but now there's an external agent pushing on the block. The magnitude of the applied force is adjusted so that the block moves to the final position very slowly. Now, why does it have to be adjusted? Because it has to be adjusted because the more you push, the more the spring pushes back. You push a little bit, the spring pushes back a little bit. You push more, it's going to push back more. So the force has to be adjusted as you slowly move the block. Let's calculate the work done by the applied force. F applied is equal to F applied in the I direction. It's minus Fs, minus the spring force. In other words, if you're applying the force, it's opposite the spring force. So it's minus kxi, which is equal to kxi. The work done by the applied force on the system is as follows. The external is the force applied dot dr, so it's integral of kxi dot dxi. So that it's the integral of kx dx equals 1/2 kx squared max. I think these are, yes, there is. Okay, this work is equal to, this work is the negative work done by the spring force for this displacement. The work is negative because the external agent must push inward on the spring to prevent it from expanding. The direction is opposite the direction of displacement. The direction of force is opposite the direction of displacement of the point. The force is directed opposite the direction of displacement as the block moves from x max to 0. For arbitrary displacement of the block, the work done on the system by the external agent is shown here. The external work is the integral from x initial to x final of kx dx, which is equal to 1/2 kx final squared to 1 minus 1/2 kx initial squared. Okay, let's do a little quick quiz. A dart is inserted into a spring-loaded dart gun by pushing the spring in a distance of x. For the next loading, the spring is compressed a distance 2x. How much work is required to load the second dart compared with that required to load the first dart? Is it 4 times as much, 2 times as much, the same, half as much, or 1/4 as much? Well, if the work is equal to 1/2 kx squared, if you double the x and it's squared, then it should be 4 times as much. And sure enough, it's 4 times as much. Okay? Remember, work is equal to 1/2 kx squared. Now, a common technique used to measure the force constant of a spring is demonstrated by the setup in the figure. We will do this in the lab. The spring is hung vertically and an object of mass m is attached to its lower end. Under the action of the load, mg, the spring stretches a distance d from its equilibrium position. So in the little block it says the elongation d is caused by the weight mg of the attached object. So we conceptualize this as follows. The figure on the right shows what happens to the spring when the object is attached to it. We can simulate this situation by hanging an object on a rubber band. In fact, we'll use rubber bands in the lab also. So we categorize this as follows. The object in the right-hand figure is at rest and not accelerating. Not accelerating means what? It means the sum of the forces is equal. So it's modeled as a particle in equilibrium. Again, equilibrium meaning that some of the forces are equal. Okay. If a spring is stretched 2 centimeters, that's 0.02 meters, by a suspended object having a mass of 0.55 kilograms, what is the force constant of the spring? Well, the sum of the forces are equal, so F sub s is equal to mg. They have F sub x, but it should be F sub s. F sub s is equal to mg, so F sub s plus mg equals to 0. Now, that you end up with Fs equals to mg, but Fs also equals minus kx. We'll just use the kx. So mg equals to kx. Let's solve for k. Well, in this case, they use Fs equals kd. So we divide both sides by d. We end up with k equals mg divided by d. And we have 0.55 kilograms, 9.8 meters per second squared, the gravitational acceleration, and 2 centimeters is equal to 2 times 10 to the minus 2 meters. And you get an answer of 2.7 times 10 to the 2 newtons. In other words, 270 newtons per meter. Because the object is in equilibrium, the net force on it is 0. Okay, we've already done that. We apply Hooke's law to give Fs equals Kd and solve for K. Yes, we did that. Now, how much work is done by the spring on the object as it stretches through this distance? Well, the work is equal to 0 minus 1/2 Kd squared. And you get minus 5.4 times 10 to the minus 2 joules. This work is negative because the spring force acts upward on the object, but its point of application, where the spring attaches to the object, moves downward. As the object moves through the 2 centimeter distance, the gravitational force also does work on it. This work is positive because the gravitational force is downward, and so is the displacement of the point of application of this force. Would we expect the work done by the gravitational force as the applied force in a direction opposite to the spring force to be negative of the above answer? Let's find out. Work is equal to force times delta R, mg times d cosine theta. Of course, cosine theta in this case is 1. So you end up with mgd. It's equal to 1.1 times 10 to the minus 1 joules. Let's compare that to the previous. Well, we can't evaluate the work done by the gravitational force on the object. If you expected the work done by gravity simply to be that done by the spring with a positive sign, you may be surprised by this result. To understand why that is not the case, we need to explore further, as we do in the next slides. For right now, this ends our discussion of the work done by a varying force. Next, we will look at section 7.5, kinetic energy, and the work kinetic energy theorem.